Hello, my dear students. In the last period, we have studied about the valence bond theory. Now we are going to study about the LCAO, which is known as the linear combination of atomic orbitals. VB theory does not tell us about the magnetic character, bond order, and bond length clearly. To understand better, new concept LCAO is introduced. LCAO full form is linear combination of atomic orbitals. According to this concept, atomic orbital combines to form molecular orbitals. Their combination is linear. Suppose two H atoms combine with each H atom has a one electron for which we have a wave function psi 1s, that is the wave function. So for H1 we have psi 1 1s1, and for H2 we have psi 2 1s2, psi 2 1s1. Thus psi 1 1s1 and psi 2 1s1 combines linearly and make two molecular orbitals. This concept is based on the wave function model or the quantum model, my dear students. You can say that. So here psi 1 1s1 and psi 2 1s1, they combine linearly and they are adding up. When they add up, they form psi MO, which is known as the psi molecular orbital, which has less energy as compared to psi 1 1s1 and psi 2 1s1. But when they linearly compound and when there is a subtraction, or when uh, wave function 1 is minus or wave function 2 is minus from wave function 1, we get the new kind of molecular orbital, which is known as psi ABMO. It simply means a psi antibonding molecular orbital. This antibonding molecular orbital, which is formed by the linear combination of the two wave function, it has more energy from as compared to the two various atomic orbital from which it is formed. So if the linear combination is of positive type, then the newly formed molecular orbital will have lower energy as compared to the energy of those orbital from which it is formed. But if the linear combination is of negative type, then the newly formed molecular orbital will be known as the antibonding molecular orbital, and it will have higher energy as compared to those atomic orbital from which it is formed. So linear combination means psi 1 plus or minus psi 2. Now let us understand the same with the figure. So you can see here that as you move up, the energy increases. We have the energy. We have 1s orbital at this energy. The same energy 1s orbital is there. So this is the 1s orbital of H1 atom. This is the 1s orbital of H2 atom. Due to psi 1 plus psi 2, we have sigma BMO formed. This sigma BMO is sigma bonding molecular orbital. This is what it is known as the sigma 1s2. We call this orbital, we call this molecular orbital. So here we are expressing the H2 molecule. So H2 molecule will have the molecular orbital. So the lowest energy molecular orbital that can be formed is sigma 1s2. Now why do we call sigma 1s2? Because two electrons are present, but we just call it sigma 1s. Sigma 1s is formed by the linear combination of psi 1 and psi 2 when they add themselves. But sigma star 1s, you can see here that we have sigma star 1s, which is an anti-bonding molecular orbital which has higher energy than both these 1s orbital, is also formed when there is a subtraction between the two wave function psi 1 and psi 2. And due to this subtraction, my dear students, we can easily understand that the newly formed anti-bonding molecular orbital has higher energy as compared to these two 1s orbitals. So this is how, my dear students, according to the LCAO, linear combination of atomic orbital, these atomic orbitals combines linearly to form the molecular orbitals, and there are two types of molecular orbitals formed. One is known as bonding molecular orbitals, another is known as anti-bonding molecular orbitals. Bonding molecular orbitals have lower energy as compared to the energy of the atomic orbital from which they are formed. Antibonding molecular orbital will have the higher energy as compared to the atomic orbital from which they are formed. Antibonding molecular orbital are formed by the subtraction, whereas bonding molecular orbitals can be formed by the addition of the wave function. When from 2H atom, H2 molecule is formed, molecular orbitals are formed from LCAO, and we can write that the electronic configuration of H2 molecule is sigma 1s2, sigma star 1s0. These two electrons which are present in 1s, according to the Aufbau principle, they first goes to the lower energy level, and the lowest energy level here is sigma 1s. So both the electron from 1s and 1s, they goes and filled into the sigma 1s orbital with the opposite spin, exactly following the rule of Aufbau and Pauli's exclusion principle. And this is how, following these rules, the electrons are filled even into the molecular orbital. So now we may even write the electronic configuration for the various molecules. So now, according to this LCAO concept, a new theory is introduced. This new theory is known as the molecular orbital theory, or MO theory. According to this MO theory, my dear students, we can understand that atomic orbital combines linearly to make molecular orbitals. The order of energy of molecular orbital up to 14 electron is given here. As you might have learned the order for the Aufbau principle, I will request you and suggest you to learn this order even. So for 14 electron, we can have the order sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2px is equal to pi 2py, sigma 2pz, pi star 2px is equal to pi star 2py, sigma 2pz. Same way, if the number of electron in the molecule is more than 14, then the order is slightly changed. This sigma 2pz comes forward. So the order would be sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, pi 2px is equal to pi 2py, pi star 2px is equal to pi star 2py, and then sigma 2pz. According to the molecular orbital theory, we can calculate the bond order. And to calculate the bond order, we have the formula number of electron in bonding molecular orbital minus number of electrons in antibonding molecular orbital divided by 2 will give us the bond order. We know that bond order is directly proportional to the bond strength or stability, and bond order is inversely proportional to the bond length, my dear students. So this is how we can understand about the concept of molecular orbital theory. Now whatever I have said you, or whatever the order I have explained, I am going to explain this to you once again. But before that, let us understand the magnetic characters. If there are unpaired electrons present into the molecule is paramagnetic in nature. But if all the electrons in the molecule are paired, we will call it diamagnetic in nature. If the bond order is 0, my dear students, molecule is not possible. Remember that if the bond order is 0, we can easily say that the molecule is not possible. Now let us study how from the atomic orbitals, these molecular orbitals can be formed. So first we shall look into this formation of the atomic orbital from the molecular orbital. Let us look particularly in up to first 14 electrons, my dear students. So just to make you understand it well, I'm taking, or I'm just encircling the area that we are going to study now. You need to focus your attention to this area. You can see that we have the atomic orbitals. These two atomic orbitals make a molecular orbital. You can see that first 1s orbital and 1s orbital of atom are placed. So from this 1s orbital we get lower energy sigma 1s and higher energy sigma star 1s. From 2s orbital of the atoms we get lower energy sigma 2s and higher energy sigma star 2s. We have 2px, 2py and 2pz for both these atoms. So total we will have 6 orbitals. So new 6 molecular orbitals are formed, and up to first 14 electron. These newly formed orbitals are called pi 2px and pi 2py. The energy of pi 2px and pi 2py are considered to be same, but the pi 2pz orbital has higher energy than pi 2px and pi 2py. These all three pi 2px, pi 2py, and pi 2pz, they all have the energy lower than the 2p orbital of the atom from which these pi orbitals have been formed. At the same time, three antibonding molecular orbitals are also produced. They are pi star orbitals. So we have pi star 2px and pi star 2py antibonding molecular orbitals. They have the same energy, but pi star 2pz orbital has little higher energy as compared to the pi star 2px and pi star 2py orbitals. So this is how, my dear students, we can understand the order for first 14 electron. I am repeating the order once again: sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2px is equal to pi 2py, pi 2pz, pi star 2px is equal to pi star 2py, and pi star 2pz. Now suppose we have the total number of electrons which are present into the molecule. They are more than 14. In this case, let us see how the electrons are filled into the molecular orbitals into the increasing order of energy. You can see here there is a slight change. Let us look at this. We have two sides the atomic orbitals. If you go up, the energy increases. So from 1s orbital, lower energy 1s and higher energy, lower energy sigma 1s and higher energy sigma star 1s is formed. From 2s, lower energy sigma 2s and higher energy sigma star 2s has been formed. But from 3 2p of one atom and 3 2p of another atom, the first we get pi 2pz, pi 2px and pi 2py. Again here the energy of pi 2px and pi 2py remains the same, but the energy of pi 2pz become lower than the energy of pi 2px and pi 2py. This is the only change that we observe if the number of electron is more than 14, my dear students. So let us understand the order of or increasing order of the energy for the molecular orbital. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2pz, pi 2px is equal to pi 2py, pi star 2px is equal to pi star 2py, and pi star 2pz. So this is the basic or fundamental idea of the molecular orbital theory. And now using the molecular orbital theory, my dear students, we are going to understand the various molecules. So let us start studying about the H2. You know, for H2 we have total 2 electrons. So 2 electrons are first filled into the sigma 1s orbital. So overall electronic configuration we can write sigma 1s2, sigma star 1s0. So, you know, for each molecule now onwards, we will write the electronic configuration, and the electron present into the BMO, we will underline with the red ink, and the electron present into the BMO, see electron present in BMO, we will underline with the green ink, and electron present into the ABMO, we will underline with the red ink. This is how you can find out the bond order. So here the number of electron present in BMO are 2, number of electron present in ABMO are 0. So bond order is equal to 2 minus 0 by 2, that is 1, and we can say there is a single bond in hydrogen, and all electrons are paired, and that is why hydrogen is diamagnetic. So now we have the next molecule He2. Total number of electrons are 4 because each helium atom has got 2 electrons. So total 4 electrons are filled. So electronic configuration is sigma 1s2, sigma star 1s2. You can see that in BMO we have 2 electrons, green pen. ABMO we have 2 electrons, red pen. And that is why bond order is equal to 2 minus 2 by 2, that is 0. So there is no bond, and that is why He2 molecule is not possible, because helium is an inert gas. Same way, my dear students, now we will study about Li2, lithium 2 molecule. Lithium, hydrogen, helium, lithium. Lithium has got 6 electrons because each lithium atom has got 3 electrons. So the electronic configuration we can write sigma 1s2, sigma star 1s2, sigma 2s2, and sigma star 2s0. So with the green underline we have 2 plus 2, 4 electron. With the red underline we have only 2 electron. So bond order is equal to 4 minus 2 divided by 2. That is 2 by 2, and that is equal to 1. And that is why there is a single bond, and all electrons are paired. So lithium molecule, when it is formed, it will have the single bond and all electrons are paired. That is why lithium molecule is diamagnetic in nature. When we look at the Be2 molecule, total 8 electrons. So the electronic configuration can be written as sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. So with the green underline we have 4 electron, the red underline we have 4 electron. Even I have written those numbers even with the green pen, green color and red color pens. So bond order is equal to 4 minus 4 by 2, that is 0, and that is why we can say that Be2 is not possible. It is a metallic solid. It does not exist as a molecular solid or molecular, it does not exist as a molecule. Same way, my dear students, we are going to study about B2. Total number electrons are 10. So the electronic configuration is going to be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. There are two electrons yet left out of 10. So these two electrons are filled each in pi 2px orbital and pi 2py orbital because they have the same energy. So the electrons are filled singly in both of them, and that is why we have the electronic configuration. I am going to repeat it once again. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px is equal to pi 2py, and that is why with the green color ink we have 2 plus 2, 4 plus 2, 6 electron. With the red ink we have 4 electrons, and that is why the bond order is going to be 6 minus 4 by 2, that is 2 by 2 and 1, and that is why B2 is possible. And when B2 is formed, B and B have a single bond. We have 2 unpaired electrons, and that is why the molecule B2 is paramagnetic in nature, my dear students. Now we are going to study about C2. So in C2 we have total 12 electron. So the electronic configuration is going to be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2 is equal to pi 2py2. Total green color underline electron are 2 plus 2, 4 plus 2, 6 plus 2, 8. Total red color underline electrons are 2 plus 2, 4. So bond order is 8 minus 4 by 2, that is 2. That is why when C2 molecule is formed, we have double bond between these two carbon, and there is no unpaired electron. C2 molecule is diamagnetic in nature, my dear students. This is how we can understand the formation of C2 molecule. Now you can see here, both the bond in C2 are pi bond because of the presence of 4 electrons into the pi molecular orbitals. You have seen that the 4 molecular orbital pi 2px2 and pi 2py2, they have 4 electrons, and that is why both the bond formed between two carbon are considered to be the 2 pi bonds. The same we can understand for even nitrogen. Nitrogen has total 14 electrons, so we can have the electronic configuration as sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2 is equal to pi 2py2, and we even have sigma 2pz2. So total the electron present into the BMO are 2, with the green color 2 plus 2 4 plus 2 6 plus 2 8 plus 2 10. In the antibonding molecular orbital we have 4 electron underlined with the red ink, 2 plus 2 4. So bond order is going to be 10 minus 4 divided by 2, that is 6 by 2, and the bond order is 3. So there is a triple bond between the two nitrogen, and you can see that N triple bond N2 is formed. Out of last 6 electrons, 4 electrons goes into the pi 2px2 and pi 2py2, and 2 electron goes into sigma 2pz, and that is why among these 3 bonds, 2 bonds are pi bond and 1 bond is sigma bond. So 1 bond sigma bond in triple bond, whereas 2 bonds are pi bond. All electrons are paired, and that is why N2 molecule is diamagnetic in nature. Now, my dear students, we are going to study about O2. Total 16 electrons are present in O2. So we can write the electronic configuration for O2 as sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2 is equal to pi 2py2, and pi star 2px1 and pi star 2py1. You are well aware that the energy of pi star 2px and pi star 2py are same, and that is why they are singly occupied. So now you can see that the green color underlined, that is BMO electron, are 2 plus 2 4 plus 2 8 6 plus 2 8 plus 2 10, whereas with the red color underlined, that is antibonding ABMO electrons are 2 plus 2 4 plus 2 6. So the bond order is 10 minus 6 by 2, that is 4 by 2, that is 2, and that is why when O2 molecule is formed, there is a double bond between the two oxygen atoms, and the electrons are in pi star orbital and unpaired electrons. So we have two unpaired electrons. You can see here that these two electrons are unpaired. So we have two unpaired electrons, and that is why our oxygen molecule is paramagnetic in nature, my dear students. So this is how, my dear students, we understand the formation of the oxygen molecule. Now we are going to study about the formation of fluorine molecule F2. So total 18 electrons are present into the fluorine. So we can write the electronic configuration as sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2p z2, pi star 2p x2 is equal to pi star 2p y2, pi star pi 2p x2 is equal to pi 2p y2, pi star 2p x2 is equal to pi star 2p y2, and sigma 2p z0, my dear students. So sigma 2pz is not been filled. Now you can see that we have underlined the BMO with the green pen. So total BMO electron 2 plus 2 4 plus 2 6 plus 2 8 plus 2 10. Now the antibonding molecular orbital electrons are underlined with the red ink. So 2 plus 2 4 plus 2 8 plus 2 6 plus 2 8. So bond order is going to be 10 minus 8 by 2, that is 2 by 2, that is equal to 1. And my dear students, single bond in F2, so you can understand there is single bond in F2, F bond F, and all electrons are paired, and that is why F2 molecule is diamagnetic in nature. Now for any two, my dear students, we can have total 20 electrons. So the electronic configuration for any two molecule, we can write sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2p z2, pi star 2p x2 is equal to pi star 2p y2, pi star, pi 2p x2 is equal to pi 2p y2, pi star 2p x2 is equal to pi star 2p y2, and sigma star 2p z2. So you can see that the green color underlined bonding molecular orbitals are 2 plus 2 4 plus 2 6 plus 2 8 plus 2 10. Same way antibonding molecular orbital electrons are 2 plus 2 4 plus 2 6 plus 2 8 plus 2 10. So the bond order is going to be 10 minus 10 by 2, that is 0, and that is why, my dear students, we can say that Ne2 is not possible. So here, my dear students, we have studied about all the molecules which have the same kind of atoms, and they were known as the homonuclear atoms. But we can explain the formation of heteronuclear atoms also with the help of the bonding molecular or molecular orbital theory. So let us study about the molecular orbital theory for the heteronuclear atoms. Let us first study about carbon monoxide or carbonyl molecule. Total number of electrons, carbon 6, oxygen 8, so total 14 electrons. So it will have the structures like nitrogen. So because nitrogen and carbon monoxide are the isoelectronic species, and we have already studied that isoelectronic species will have the same bond order and will have the same molecular orbital electronic configuration. So for CO we can write sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2p x2 is equal to pi 2p y2, and sigma 2p z2. So bond order exactly like nitrogen, my dear students. 10 minus 4 is equal to 2, that is 3, and that is why carbon monoxide or carbonyl also present as C triple bond O. All electrons are paired, and that is why CO is going to be diamagnetic in nature, which is exactly like nitrogen. That is what, my dear students, we can understand it easily. Now we'll study about some more. Let us think of NO. For NO, the total number of electrons, nitrogen 7, oxygen 8, so total 15 electrons. We don't have any homonuclear 15 electrons, so let us write the electronic configuration: sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2p z2, pi 2p x2 is equal to pi 2p y2, pi star 2p x1, and pi star 2p y0. So here, my dear students, you can see that in the BMO we have underlined the green color. So we have 2 plus 2 4 plus 2 6 plus 2 8 plus 2 10 electron. But in antibonding molecular orbital we have 2 plus 2 4 plus 1 5 electron. So bond order is 10 minus 5 by 2, that is 5 by 2, which is 2.5. It means the bond order is a fraction. When bond order is a fraction, we can easily say that it is not, or the structure of this compound cannot be easily explained by single structure, so it will definitely be explained with few resonance structures, and we have already studied the resonance structures of NO, and that is why the exact structure of this molecule can be represented by the hybrid orbitals or the hybrid structures, and we know that the hybrid structures which is formed must have or generally have the fractioning bond. So if the bond is single and double, it is going to be 1.5 bond, and if the bond into the resonance structure is double and triple, then it is going to be 2.5 bond. So here in NO we can easily understand the 2.5 bond. We have even studied that NO was an odd electron molecule, and that is why it is definitely going to be paramagnetic in nature. The odd electron which we see on nitrogen present, which is the only unpaired electron, that is the single electron we have seen into the resonance structure of NO, which makes it an odd electron molecule. This electron you can see into the pi star 2px orbital present, and this is how the explanation for NO molecule can be easily given by the theory called molecular orbital theory. So for NO, we can write that bond order is 2.5. The odd electron, the NO is an odd electron molecule, and the odd electron is present into the pi star 2px orbital of the molecule. It must have the resonance structures because bond is a fraction, and there is no clear double or triple bond found between the nitrogen and oxygen. There is one unpaired electron present, and that is why NO is paramagnetic in nature. We can even understand the formation of ions, my dear students. So now we are going to study the formation of various ions and their explanation according to the molecular orbital theory. So let us go for it, my dear students. Let us first study about NO plus. You know, nitrogen has got 7 electron, oxygen has got 8 electrons, so total 15. But due to plus 1 charge, 1 electron is removed, and total we have 14 electrons. This is very similar to the nitrogen. So NO will have exactly like nitrogen, it will have triple bond, and it will be diamagnetic in nature. So now you can easily predict looking at the number of electrons. If you think of NO minus, then the total number of electrons will be 7 plus 8, that is 15. Due to minus 1, one more electron is added, so total 16 electron, which is very similar to O2. So we can say that in NO minus we will have double bond, and it will be definitely paramagnetic in nature, because pi star 2px and pi star 2py will be singly occupied, and they will have single electron, so it will have two unpaired electrons present into it. So my dear students, now we should learn it and remember it for a longer time, that isoelectronic species, my dear students, have same characteristics in the regard of bond order and in the regard of magnetic character. So all the isoelectronic species that we are going to study will have the same bond order and will have same magnetic character. That means either paramagnetic or diamagnetic. Let us study few more ions or more species. Let's have look to O2 plus, my dear students. Oxygen has got 16 electron, but when from oxygen O2 plus 1 is made, 1 electron is removed, so total 15 electron, which is very similar to NO. We have just studied about NO, but still we are going to write its electronic configuration. But you can easily predict. Let me finish it for you, that it will have the bond order 2.5, and it cannot be explained. It must have the resonance structures, and it will have one unpaired electron, and that is why it is going to be paramagnetic in nature. Same way, my dear students, we can look for O2 plus. O2 plus will have 14 electrons, so it will be very similar to N2, and that is why it will have bond order 3, and it will have triple bond. It will not have any unpaired electron, and that is why it will be diamagnetic in nature. Same way, my dear students, when we think of O2 minus, total oxygen has got 16 electron. Due to minus 1 charge, it will get 17 electron. We did not have any example with the 17 electron. So let us write the electronic configuration. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2 is equal to pi 2py2, pi star 2px2 and pi star 2py1. So here the 17th electron goes into the into the pi star 2px2, and the unpaired electron which is present into the oxygen, out of them one pi star 2py orbital remains unpaired, and that is why there is one unpaired electron into the O2 minus 1. So here you can see that the total number of electron in BMO would be 2 plus 2 4 plus 2 6 plus 2 8 plus 2 10. The total number of electron in ABA would be 2 plus 2 4 plus 2 6 plus 1 7. So you can write the bond order is equal to 10 minus 7 by 2, that is 3 by 2, that is 1.5. So here the bond order is between 1 and 2, that is why it is known as the 1.5. Here you can see that one unpaired electron, and that is why it is paramagnetic in nature. Now, my dear students, if you look at O2 minus 2, it will have total 18 electrons. It will be very similar to F2, and that is why we can easily say that the bond order is going to be 1, and it is going to be diamagnetic in nature. So same way, my dear students, we can arrange these all the species that we have studied about O2 into the increasing order of their bond order. So you can see that O2 minus 2 has a single bond, O2 minus 1 has 1.5 bond, O2 has 2 bond, O2 plus 1 has 2.5 bond, and O2 plus 2 have 3 bond, 3.0 bond, or 3 bond, my dear students, we can understand. And this is how we can understand the increasing order of bond order. But we know that bond order is directly proportional to the stability, and that is why we can say that O2 minus 2 is less stable than O2 minus 1, O2 minus 1 is less stable than O2, O2 is less stable than O2 plus 1, and O2 plus 1 is less stable than O2 plus 2. That is what we can predict according to the molecular orbital theory. Now, my dear students, we are going to study a few more species. Let us look at the N2 plus 2. So in N2 there were total 14 electrons. So N2 plus 2 will have 13 electrons. So the electronic configuration would be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2 is equal to pi 2py2, and sigma 2p z1. Remember, here there is one unpaired electron. The bond order according to the green underline, 2 plus 2 4 plus 2 6 plus 2 8 plus 1 9, and the ABMO 2 plus 2 4. So bond order is going to be 9 minus 4 by 2, that is 5 by 2, and that is 2.5. Same way, my dear students, here we have one unpaired electron, and that is why N2 plus 1 is going to be paramagnetic in nature. But when we look at N2 plus 2, it is a 12 electron. It is very similar to C2. The electronic configuration is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2 is equal to pi 2py2. Bond order is going to be 2, and there is no unpaired electron, and that is why it is diamagnetic in nature. And both the bond in N2 plus 2 would be the pi bond. Same way for N2 minus 1, we have 15 electrons, which is very similar to O2 plus 2, and that is why the bond order is going to be 2.5, and it is going to be paramagnetic in nature. Same way for N2 minus 2, my dear students, we can have 16 electrons, which is very similar to like oxygen, and that is why the bond order is going to be 2, which is paramagnetic in nature. And this is how, my dear students, we can understand the various molecule or various species related to nitrogen we can study. Now you can see here, my dear students, that the various species that we have studied for nitrogen, they can be seen on your screen. So if you look at N2 plus has a 2.5 bond order, N2 plus 2.5 order, N2 plus 2 will have the bond order 2, N2 minus 1 will also have 2.5, my dear students, the bond order, and N2 plus N2 minus 2 will have 2 bond order. So here we have N2 plus 1 and N2 minus 1 have similar bond order, that is 2.5, and N2 plus 2 and N2 minus 2 have similar bond order, that is 2, but nitrogen has got 3 bond order. Once again I am repeating, N2 plus 1 and N2 minus 1 has a bond order 1, N2 plus 2 and N2 minus 2 has a bond order 2.5, and that is why, my dear students, we can easily understand that the bond order for N2 plus 2 and N2 minus 2 is equal. The bond order for N2 plus 1 and N2 minus 1 is equal. And N2 has got the highest bond as compared to all these species. And we know that bond order is directly proportional to the stability, and that is why the N2 is the most stable among all these species. Then N2 plus 2 and N2 minus 2 are less stable as compared to N2 plus 1 and N2 minus 1. And the highest stable species among all the nitrogen species are N2. Same way, my dear students, we can even understand few more species. We can look at CN. For CN, my dear students, we can write or we will study CN into the some next period. I hope, my dear students, you are enjoying your studies. Happy learning.